In this session, we will explore the four very commonly encountered discrete distributions and that are kind of standard members in our library of distributions to apply. Um, and they are standard more because they are commonly encountered in most introductory probability and statistics courses and therefore in the exams. But of course they are also there in the exams more because they are also important in real life. So we will encounter these the usage of these distributions and be able to then apply them in a clever and appropriate way. Let's begin with the easiest to understand distribution. And as we mentioned before, each of these distributions, when I say distribution or a distribution, I actually just mean the whole class of distributions. Because when we say, for example, Bernoulli distribution, it comes with an input parameter. So a parameter is like a tuning knob on your radio. By turning to different frequencies, you listen to different content. But then they are all radio programs, isn't it? So it's like a category of information. Likewise, when we say Bernoulli distribution, we are actually talking about a whole huge class or category of distributions that are all following some sort of a Bernoulli style. And by that, we mean we tune that to a specific distribution, to a specific histogram with this parameter P. And P is called the probability of success here. For example, I give it a 0.3, meaning in my Bernoulli distribution here, I want the probability of success to be 0.3. So remember that the distribution can be rendered visually visible by a histogram. So we will then draw a height of 0.3 where the success is represented by 1. Now, a 1 here is just a label, and of course, it has the additional nice property of having something versus having nothing, right? And in certain cases, the decision between having none and having one or many is a very critical one. So we will use this convention: 1 to represent success, 0 to represent non-success. So here we specify, we require that the probability of success is 0.3. Now, why is it 0.3? Because in the past 100 observations, we noticed that 30 of them were successful. Okay, so success here doesn't have to be a happy thing. Success here can be detection of cancer cells, can be success can be anything that is interesting to the observer or the person studying this experiment. So success can be company failures during financial crisis. So I observed yet another one, yet another company closure, yet another one, right? So I counted 30 out of 100 SMEs, for example. So P is probability of success, but you got to take the word success very generally rather than the English sense of it. So once we define this to be 0.3, the other bar has to be 0.7. The heights must add up to 1 because it's a must for distribution to hold. Now, having said that, why do we need it when it's so simple, right? It's not just a class starter, as if we don't have a better beginning distribution to talk about. So we invented one as simple and as useless as it seems. Not really. It is very useful because it involves just simply two states, two mutually exclusive and exhaustive outcomes. Now, while that may seem too little, actually it is very common, isn't it? When we have 10 potential choices to make, a very natural thing for us to do is to try to group them, yeah, into somewhat similar alternatives of each other. And if we manage to get down to 5, we may try to group further down to 3 usually, but let's say we narrow it down to 2. Yeah, and the rest were just minor variations that wouldn't really affect your decision anyways. So that is down to 2, left or right. Do or don't, yes or no. So oftentimes it is human nature to try to summarize the available options down to two choices, maybe three, but let's say if we summarize down to two choices, then we'll find that Bernoulli distribution has got plentiful application areas. So should I buy this stock or not? That's yes or no. Should I buy or sell? Because I'm not going to choose doing nothing. I'm going to just buy or sell. Should I buy or don't buy? That's another yes or no. So it depends on how you phrase it. It doesn't have to be two equal share outcomes. It can be one is, quite obvious, quite ready, quite attractive. The other one is less attractive. Should I study or sleep? Right. So there's no bigger or smaller sense to studying or sleeping. Maybe because you inherently prefer sleeping, so sleeping seems like having a bigger chunk of your mind share, but they are just 2 points. Yeah, 2 points on the x-axis. And again, as I cautioned in the previous video, that for discrete distributions, when we draw it in histogram, the width of it actually has no meaning. So here for visual attractiveness, it is being fattened up to occupy the chart. But the actual information is just the point here, right? Just underneath 0.7 and just underneath 0.3. Just 2 points to indicate Bernoulli distribution. Yeah, so it's got many, many uses whenever there are two state outcomes and it involves a choice, yeah, a selection between yes or no, do or don't. Now, the P here is probability of success, and oftentimes we gather the value from past events. And so it's not surprising that we associate relative frequencies, proportions measured in the past, percentages measured from past census, survey, or research data. Yeah, okay. So just a quick example that I thought of, a quick look at a country, whichever country, a country's population, we can quickly gather what's the percentage of male versus the entire population. So it may not be exactly 50%, right? And depends on the year that you're talking about. So it may be that in a particular country for a particular year, the ratio, the percentage for male is 48%, let's say. When you tour that country right now and you happen to visit the hospital and here comes a baby and you are not sure about the gender and you are going to make a guess, right? So should you guess that the baby is male or female? Well, looking at that sort of a prior probability where we did a rough estimate based on existing population, 48% male, right? So if our success is defined as the baby is male, then P equals to 0.48. And we can then draw a chart, right? So 0.48, female is 0.52. So now you can make decisions. If you're making a bet that it is a gender that is more likely to be for this particular baby, then you say, I'll bet it's a she, right? So that's because it's 0.52 versus 0.48. So it's just a quick example to show you how we may deploy this Bernoulli distribution. As for the formulas, they are listed here, and just to make it mathematically complete and nice, otherwise it actually doesn't have to be so horrendous, right? So we know it's just two numbers. We can remember them. But if you want to express in the single formula functional form, then p to the power, if x is 0, then this is 1. P to anything p anything to the 0 is 1, and 1 minus 0 is 1. 1 minus p, that's 0.7, right? So that's a long way to get 0.7. And expected value is going to be p. So interestingly, the mean of this Bernoulli distribution is the height of the one here rotated down, right? So the height becomes the x-axis and the mean is 0.3. And you can see that if you put a pivot somewhere along between 0.1 0 and 1, and so you put around 0.3, maybe here, you'll find that roughly speaking, it looks visually balanced, right? Because there's a big chunk of mass here, and then kind of balanced by the other chunk of mass here. Should balance off. So the exact balancing point is the expected value positioned on the x-axis, and that's p. For variance, we have to derive using the standard definition. That is expected value of x squared times the distribution, right, minus the square of expected value, which is p squared. So that's for Bernoulli distribution.